Good morning. My apologies for the delay. We had some technical issues. I'm Brant Olson. I'm a senior manager with Deloitte in our AI and data team. Today, I'm going to be talking to you about the work that we're doing with simulation technology, in particular in the railway industry. Go ahead and bring my screen up. Great, thank you. So the work that Deloitte has been doing with transportation is around simulation technology, and we're using artificial intelligence, machine learning, and simulation technology to have a new look on the transportation network and how we can make it more efficient and run better for everyone that uses the railway, myself included. I love the trains. Before Deloitte, I've been in public transportation for over a decade, working in heavy railways, light railways, so trams, and also metro operations like the London Underground. So this is something I love talking about. So I'm really pleased to be here with all of you today to talk about this. The solution that we've developed for the railways before the pandemic was really focused on three key areas of capacity. So how do we get more trains on the network to allow better performance, so you don't have to stand up in the carriage and not get a seat. So how to get more capacity onto the network. About performance, making sure that the trains are on time, because no one likes standing around waiting for a train, wondering when it's going to turn up. And then the asset and maintenance costs. So running the railways is expensive business. There's never enough budget for all the maintenance work that goes into it. So how do you prioritize your maintenance budget and make sure you're focusing on the assets that are the most critical for the operation? In the post-pandemic world, that's changed a bit. So we've had some different stresses and issues coming into the railways. So no passengers or very few, and passengers starting to come back. That's asked some different questions of us on the analytics side when we're looking at, how do we do the timetable? So we're doing the planning of when those trains arrive, the timetables. How can we do that more efficient, be more dynamic, change to it? If you don't know, in network rail today, it takes 2 years to try and plan a timetable. With the pandemic happened, it's been not enough time to react to that. You can't have 2 years. So we're working with network rail to speed that up, to get it down to months, to react to the constant changing, flexing situation with the pandemic. When we have that new timetable, then it becomes a question of capacity. So do you have the trains to run those services? And do you have the staff? Again, especially during the start of the pandemic, when a lot of staff were shielding, we might have had a new timetable, we might have had the trains, but we didn't have the staff necessarily available to run those services. So a lot of different questions have been asked of us in analytics and simulation, and how we can support those kind of questions. And then we've had some different changes too. So with the pandemic and the loss of revenue, which you've all seen in the newspapers, that's affecting the railways. And so there's been a real focus on when we're making investments in the railway, are we making the right investments? So what have we done? So Deloitte have developed a solution for the railways, which focuses on those key areas I talked about on railway. So planning, so timetabling, so how do you have efficient timetables? Assets, so understanding what are the key assets on your railway. So if something breaks, what is the impact on services, and what are the key assets that need to be focusing on? And a controller timetable, which is all about disruption. So how do we get the services back up and running? And then the railway environment, you have a really key challenge, which is you have a data estate and systems that go from the 1980s all the way to present day. That provides lots of different challenges in terms of working with that data, making use of it, and providing insight. To work with that data at Deloitte, we've built a unified data model, and that allows us to take the operational information, so whether that be from a Alstom or a Hitachi system or Thales, which you might not be familiar with, but those are the operational systems that sit in the railway. Combine that with maintenance data. So you have different maintenance systems, which are provided by IBM, or you have Ellipse, which is the main maintenance system used by Network Rail, or SAP Material Management. So that's where all your maintenance information sits. It's really about bringing those two data sets together, because before they've been isolated. Bring those two data sets together, drive insight, and then bring other data sets into there. So bring in weather. So what's the effect on weather on the railway? What's the effect on weather, not just running it, but also on the assets, and how that all intertwine, and getting real insight into that. So here, what I'll show you is our asset toolset first. So what you see here is the Clapham to Waterloo Junction area. This is the busiest part of the network in the UK. And when we first sat down with Network Rail, the challenge they had was they know not vaguely, they have a pretty good idea what their critical assets are, and they call them their golden assets. But they weren't 100% sure. And so one of the challenges that they set to us, so Deloitte, was, can you demonstrate to us what are truly the critical assets on the network, not just the ones that we think are. And so that's what we set out to do. And again, here's a Clapham to Waterloo Junction area, and the green, yellow, and red. The red is the more critical assets on the network. So we just drill down, have a look at that, and say, well, what is that asset? What is it so critical about it? And what you can see here is we have a track circuit, which is very important to that area. And what a track circuit does, if you're not familiar, track circuit lets you know where on the railway the train is. If the track circuit fails, I can't see the train on the railway in the systems I'm using. That brings that whole line to a stop, and it can have a cascading effect, stopping all the services around it. So very impactful. And in the Waterloo area, it's an impact to Network Rail to the tune of £3.6 million. So very critical that this particular track circuit stays up and running. How do we drive that criticality? Again, it's taking that operational data and that maintenance data, bringing them together. So understanding how many movements of vehicles go across that railway, and then understanding if that fails and the possibility, the likelihood of that failure based on the condition of the asset. That's what gives that insight to say, okay, well, this is your critical asset, so you really need to be focusing on that. And that criticality for Network Rail, and it's important to understand that there's different ways to look at criticality in the railways. For Network Rail in particular, it's around the cost per minute. So if that asset fails, what's the cost to the business? PPM, which is the public performance measure. So what's the impact on passengers if that asset fails? So how many services get canceled or delayed? Fatality weighted index, which is about safety. So if that asset fails, what's the chance that could cause a derailment or other injury? Then the delay incursion. So how many minutes of delay are attributed to that asset when it fails? And then again, the movement, very, very key. So that gives us our asset criticality and insight. And again, a heat map of the assets, so bringing it up, making it very obvious to Network Rail. What are the key assets? This then feeds back into the maintenance budgeting. So again, I can focus my limited maintenance budget on the assets that are most critical. That's really, really key and to understand that. And what is the nice thing about this, not only can we understand the assets as they are today, we can understand the assets criticality in the future. And what I mean by that is, as I explained earlier, there's a 2-year timetable planning process. So, the movement of the vehicles, which is the biggest wear and tear on the network, is being planned 2 years in advance. Using that theoretical timetable, that 2-year timetable, we can bring that into the model, and we can extrapolate in the new timetable, if there's a shift in the movements of vehicles, how's that going to impact the assets, the underlying track and track circuits and signals and switches? What's going to be the impact on that network? And here what we have is we've done that. We roll forward. So we've taken a 2-year planned timetable, so 2 years out, rolled that forward and say, okay, in that new timetable, is there a change in the assets? So here's my most critical assets, and here's my least critical assets. And that's really driving insight for Network Rail to when they're doing their forward planning and thinking about their maintenance schedule and their renewal schedule. So again, bringing more efficiency into the railways. So that's it about assets. I'm now going to turn over to timetable planning and what happens with timetables. So here you see a timetable being loaded. looking at the different scenario options that can happen around the timetable, time of year, weather, special events. So if there's a football match on at Cardiff, at the Millennium Stadium, big impact on the town centre. So looking at different impacts that can affect the performance of the railway. And then we lit up a timetable. So if you're not familiar with timetabling, I mentioned most people on this are not. This is a timetable diagram. So this is the trains. So there's a starting station, finishing station, and it's the trains going up and down on the timetable from station to station, back and forth. And it's a timetable diagram. What we've done working using artificial intelligence and machine learning and simulation technology is to be able to analyze the timetable and understand straight away when I'm proposing a new timetable where there's going to be problems. So using the pattern recognition that you have from machine learning, I can use the past timetable, the performance of that past timetable, compare that to a proposed timetable, and know straight away there's problems in this timetable, these red spots. I can see there's hot spots. So how do I make that more efficient? So how do I do that? So this is where we bring in the simulation technology. So we're running that simulation against that timetable to optimize it and come up with the best option for the timetable. We've done this now just shy of 3,000 times, and it gives us an optimized timetable. This is what it looks like when it's doing the optimization in the background. So this is the what's happening in the background when we're doing the optimization. And so what you have here, apologies. What you have here is the Trans-Pennine network. So this is from Leeds down to Manchester. And what's great about simulation technology, and where it's a big step change versus previous modeling technology, is that you're bringing in a much higher fidelity by using simulation. So this network, this is the physical representation of the network as it is in the ground. So it's the curvature, the gradient, exactly as it is in the ground. So you bring in the physical network as it is into the simulation. And then you're also using the machine learning and AR, which gives you probabilistic modeling. And what I mean by that is that the previous generations of tools, they would look at the average possibility. So on average, how does a train behave during the course of a day? On average, what happens? Anyone that takes a train on a regular basis or works in the railways knows that there's no average day. There's lots of variables, things happen a lot. And so artificial intelligence, machine learning gives us the possibility to have probabilistic model. So what's probably going to happen on the day? What's the most probable thing that's going to be happening on the day? The simulation engine has the physics, which gives it a deterministic. So the trains can accelerate faster than it's possible. They have to brake in the same manner that they would on the railways. And then you get real high fidelity in that model. So we have the train running on the tracks. This is happening in terms of a fidelity that is within 15 seconds. So when we do our modeling today and then we test it against reality, our predictions are coming in within 15 seconds of reality. So very high fidelity modeling. And that is what really starts to unlock the capacity and the performance of the railway network. And here, just to show you, so this is the throttling curve, so brake acceleration curve. With probabilistic modeling, you're capturing that detail. You also capture the driver behavior and the on the infrastructure into the machine learning, and then it's reflected back in. So you have the curves as it were, whereas in average modeling, this will all be smoothed out. And so you lose the fidelity as a result of doing that. So we've done the simulation of the timetable. We can still see there's problems in the timetable. So in Network Rail, we've developed a package to go in and analyze those pinch points. So if we can't find a way around it by optimizing it, we then go in and see what's stopping us from getting a final optimization. So that's when we go into our analytics package. And we start drilling down to what are called timetable planning rules. So in the way the timetable is constructed is lots of little rules, or if you in any business setting, it'd be your business rules to run your operation. So in the railway terms, it's timetable planning rules. And those are things like dwell times. So how long does the train stay at a station before it moves on to the next station? How fast can the train actually move across the infrastructure? Does it run at 60 miles per hour? Does it run at 100? what's the gap? So it's called the headway. So how much time do you have to leave between the trains for safety? So there's lots of little planning rules that go into creating the timetable. And what we provided to Network Rail was an analytics package to let them go in and investigate those timetable rules and understand which timetable rule isn't working. So which business rule isn't working, which then in turn is impacting the performance. What we have here, this is the absolute capacity of the railway network. So if there was no constraints, no safety issues, nothing, this is what your absolute capacity would look like. Of course, you're never going to get in there because you have to have a safe running railway. The green is what Network Rail has been achieving with the timetable as it was. So there's inefficiency in the timetable. We can see that. And the orange is what the analytics is telling us, saying that there's more capacity in the railway than you're getting. And it might necessarily mean putting more services on. It could be that the timetable is inefficient and the timetable is causing so much disruption that you're losing minutes. So all those delay minutes. So by removing those delay minutes, you move up the capacity. So one of the things we look at is timing point to timing point. So in Network Rail language, it's tip lock to tip lock. So timing point location to timing point location, which is typically one station to another station. If they're far away, so out in branch lines in Wales and Scotland, where you have long gaps between stations, then you have intermediate timing points. But in a dense urban network, it's station to station typically. So we go down, look at that and say, okay, what can we understand inside the timetable is not working? And we're looking from timing point location to timing point location. And what I was talking about, so we can see here, there's big variability in the dwell time, which isn't being reflected properly into the timetable. So we have a disparity between what the timetable says in terms of how much dwell time, so how long I'm going to spend at the station, and then what's actually happening on the day. When you have that disparity in the timetable, you get what's called a dwell time propagation wave. So if the train is supposed to be at one station for 30 seconds, but it's there for 45 seconds, then it's late at the next station, the dwell time's out, and then it keeps going. And so you get this a wave that just goes down the line and has impact on there. So it's really important that these dwell times are right. With the analytics, we can see that they're out, and then they start doing something with it today down in Network Rail to rectify that. One of the other things we look at with timetables is called the sectional running time sequence. So section to section. So that typically a section is from signal to signal in the railways. And you're looking how fast the vehicles can move across that section. So what's the permissible line speed? So is line speed 60 miles per hour for that section? And then how quickly are the vehicles actually moving across that? And here you get also lots of problems when you're trying to develop a timetable. Again, it starts 2 years in advance, and then I get onto the day. When those 2 years, what can happen? The trains that were running that have gotten worse, so they're in poor repair. They're not going as quickly as they should be. So anyone that was fortunate enough to go around on pacers in the north of England know that those are not very fast, and they're 50 years old, and every year they just degrade, and thankfully they've been taken out of service. But you see that kind of degradation in the vehicles, and that impacts the sectional running times. You have the same thing with new vehicles. So again, I've done my planning for my timetable 2 years in advance. The timetable comes out, and now I've got new vehicles in service. We can actually go faster or maintain the timetable. And so that also causes disparity in the timetable, and that's your sectional running times. And again, we can see there's disparities here with what should be happening, what's actually happening. And so you go back in and look and say, okay, what's the problem with that sectional running time? What's happening? Is it the vehicle? Is there a problem on the infrastructure? Maybe there's been a temporary speed restriction put in for some maintenance work that engineering's put in place, but they haven't told the planning team. And so there's lots of little things that you have to go tease out in the timetable. So that's kind of a big summary. There's a lot more that we do with timetables. There's lots more pieces that we go and look at. We won't cover all of that today. The next piece we'll be looking at is disruption events, which cause lots of delay on the railway. And again, using simulation technology and AI, we're looking at ways to improve that disruption, to get the services back up and running quicker using digital approaches. So what you have here is the leads area. And what we're doing is we're digitally replaying a day in and around leads, and particularly a day that had disruption on it. So we can see that there's a disruption events happening, a broken down vehicle, which is causing a block on the line. And just replaying that in a digital environment, simulation environment, so we can understand what's happening there. Yeah. So we repair that environment. Now we ask the questions of what could we have done to have a quicker recovery? What were the different choices? So you have, they're called pathing options, so different ways the train can go, and the operator has choices when it's time to resolve disruption. So which way do I route the services in order to get around the disruption? What are the optimal choices there? Here we can see the choices that were taken. And then we do a computer simulation against those and try and optimize those. We can see that there's actually different paths, different choices that the operator could have taken in terms of resolving this disruption. So the optimal actually would have been routing in around leads, and that includes for the passengers to get them to this is Church Fenton Street, so routing around to Church Fenton Street and then catching a service going back. So you would have a much better option for the passengers. So here, the disruption caused 3 hours of delay. By rerouting around that vehicle that was stalled out, having passengers come back again, you could have got that disruption resolved in just an hour and a half. So big difference. And that's just kind of the insight that we're seeing when we bring the simulation and AI technology, because we can replay it, we can visually understand it. And it really makes a big difference when you're looking at these types of events. We're also using this to help build new infrastructure. So we're looking at new infrastructure and what's the best optimal infrastructure moving forward. So Deloitte, working with the Department of Transportation and Network Rail, we've been modeling the Transpennine route upgrade and the different infrastructure choices you have up there. So whether it's adding additional platforms at leads, putting different pathing options so that fast trains can pass the slower ones, or different types of signaling technology. So you have a new signaling technology, which is called ETCS, which is the European Train Control System. It's an all digital train control system, which has some real efficiencies. And right now, the Department of Transportation is looking at all those options and looking at what's the best thing to invest in terms of those infrastructure, the physical tracks themselves, the signaling systems, timetables. And working with Deloitte, again, we brought this new approach to modeling in. So we have up top is your traditional approach to modeling, which is using that rolling average, and you can see it's really flat. It's not incorrect, so the start and end of the journey time, they're not too far off actually. But when you use the probabilistic approach, you see what actually happens on the railway. So this peaky up and down is what's actually happening on the railway, and that's the actual performance you're going to get. So the surprising thing is when you use the rolling average, is actually you get a much more optimistic view of the railway capacity than you do when you use the simulation technology. This actually gives you closer fidelity. So we're within 15 seconds when we're doing the modeling using AI and simulation, but it actually gives you a much more pessimistic view about how many services you could run on that network. So I'm going to pause there and hand over to my colleague, Maria, who's going to give you some more of the technical detail behind the scenes of how it all works.
Hello, good morning from Deloitte office in London. I'm Maria and I'm a manager in consulting in London. Today I will just continue talking about more details about the story that Brant has already made a big introduction of. Brant, if you can just keep the slides, please, that would be great.
Great, no problem.
Thank you. So I serve as a technical lead of Motion Simulator, and I'm very enthusiastic about developing new features and presenting the old ones to the client and then conducting any work that is necessary for our clients. How do we do this? In simple words explained, we have a cloud-based technology, but also Tableau-based technology for visualization of these results. Our motion simulator can utilize the cloud technology to present near real-world operations in this advanced simulator, and also to introduce any sort of train operating parameters and introduce external variability, example, adverse weather, incident mapping, etc. There are a couple of main inputs to the simulator. Obviously, the main one and the most important one is the timetable, which we expect that the trains are going to respect as much as their physical characteristics are allowing and as much as the probabilistic model is allowing. The next component would be probabilistic of transversal time from bird to bird, which is typically from signal to signal, or predicted transversal time for the train to pass from one ETCS block to another ETCS block in case that we are implementing ETCS technology. A machine learning model is pre-trained before simulation, and then only the output from machine learning model is becoming an input to simulation. Another part, and very important one, is the one that we are looking at this slide, is the track geometry, which normally we need to create from the scratch. How do we do it? Typically, we use OpenStreetMaps, which are available to anyone. And they have the current situation of all the ways and all the railways in the UK. We use Python and specifically command bbox to select and extract part of the track or the network that we are mostly interested in. It is very similar to select and crop tool in any visual tool, for example, Paint. Once we select and crop whatever part of the network we need, we simply select line strings only using Python code so that we can discard any sort of lines and ways that we don't need for these purposes and keep only the wanted ones. And that's not obviously the end. After that, we would need to test the geometry in some other visualization tool, for example, Tableau, just to make sure that our lines are correct. And then in the end, we need to add directions, birds, signals, and name those ways. Also, we need to include the line speeds for all the tracks and export everything to GeoJSON, which is something that our Unity simulator can then read and process. So once we have passed all of these input files to Unity simulator, then the simulation can start. What happens there is that Unity will convert the geometry longitude and latitude coordinates into something that is called the world coordinates, which is Unity's local transformation coordinate system. And then we can follow the simulation, which we just saw on the previous slide, and observe how the train is moving from one station to another, or how any train is coming into the network and in which order as well. We also have the ability to speed up the simulation and to perform multiple simulations faster than in a real time, but still obtain all the characteristics like we are running the simulation in the real time. That way we can analyze many timetable options in a day, and also analyze scenarios, what if, which is the where this simulation is very very useful. Once the simulation is completed, as an output, we are getting the log file. Log file needs to be interpreted again using code because it is not really human readable. Then from the log, we can assess the results and see what would be the average minute lateness comparing to the expected timetable schedule. But we can also see where any sort of error, train collision, wait time on red signal, or wait time for the next ETCS virtual block to become available. So the possibilities of this simulation are really big, and we keep expanding the tool every day. Thanks, Brant. That's all from me for today.
Great, thank you, Maria. And just a quick summary in terms of what we've been delivering today for Network Rail in terms of the impact of bringing in simulation technology, artificial intelligence and machine learning into the Network Rail environment. So in terms of on-time minutes, we've seen 1.6 million more passenger journeys on time since this technology has been implemented, 18 million minutes of delay avoided, and the impact on Network Rail has been 12.5 million in terms of operational expenses, and that's mainly composed of fines that they wouldn't have paid otherwise because of the lateness of the services. That's all we have for today. We have some time for some questions, so we'll go ahead and I'll stop sharing and see if we have any questions that have been posted.
I think we have just that one from Andrew, which I think you covered because he posted that quite early on. The how does it integrate with the traffic management, stock and crew, and Network Rail's integrated timetable planning tool. I think you actually covered that after he posted it because that was quite early on in the session.
Yes, yeah. So we're working today with Network Rail on that integration with the stock and crew. In fact, I'm working on a project looking at just that at the moment. So you're probably familiar with the stock and crew tools that they have. So there's the main one is Attune, which is provided by Belvidia, Traxxas Belvidia, and it's really providing that data. So the challenge that exists today in Network Rail is the berth level data. It's messy, it's inconsistent. So we're working in the first instance to get the berth level data available so we can have a network model, and we're building that at the moment. And then the next step that we're going to be doing is actually bringing that model and making it available so you can start testing stock and crew questions, kind of what if scenarios of do I have enough the right stock, the right crew in the right place to run the timetable. So we're looking at the train service specification. So how many pathing options are available for the train operating company. I might say on a route across the north of Wales, you can have 4 services an hour. Is that actually the case? And we're using modeling to solve those questions, which then has that impact on crew and stock availability.
I love Lisa's question. What do you most enjoy about your roles? I mean, it feels incredibly satisfying. The impact you guys have is so tangible. There's the data element, but also the human impact. But Brant, do you want to go first? What do you enjoy most?
For me, it's I have to say I have one of the luckiest jobs in the world because I love data and I love trains. And I get to work with both on a daily basis. So what can I ask for?
Maria?
Oh, very similar to Brant, but I'm very driven by technical challenges of the simulator and the machine learning models.
Is it also a challenge you feel is always evolving? It's never one that you will
Absolutely.
solve. Yeah.
Absolutely.
I think that's. Are there any more other questions? Going to just check on the chat and see if there's anything else. I think that's everything. Thank you so much for being a part of Bristol Tech Fest.
Great, thank you.
Thank you for having us.
Have a good day, everybody. I shall stop the broadcast. Thank you.
Bye.